Okay, so thank you for being here to the GstAnalytics presentation. My name is Daniel Morin, and I'm a senior software engineer at Collabora. I've been working on multimedia for about 15 years, and with a focus on analytics in the last 5 years. So So this would be the outline of the presentation. We'll go a little bit through what is an analytics pipeline, why would we choose GStreamer to do an analytics pipeline, the new and improved tools in GStreamer, and last is the tensor negotiation and auto-plugging of analytics element. So basically, from a very high level, an analytics pipeline is something that gets data and extract insight from it, So here's an example. So this is an example taken from the agri-tech world, where you have crops that are growing into a vertical farm, and you would like to find unhealthy specimens, and then you can have cameras that are monitoring all the environments to find the unhealthy one. Another example could be just to like a very large area, for example, in an airport, and you want to locate a person. So you have multiple devices deployed all over the area, and all of those need to be producing analytics. They need to be centralized, and also in some case have some human interaction that is part of the process. Others more multimedia focus, for example, ML-based video compression, ML-based dubbing, and virtual privacy wall is all example of analytics pipeline. Here's an example of an analytics pipeline that it showed that it's not just one element that is doing the analysis. It's actually break down in multiple elements, and GStreamer is very rich of already with his existing elements. For example, we have the acquisition, pre-processing. There's a lot of capability already existing in GStreamer for that. But for the element that are actually doing the analysis, for example, the inference tensor decoder, here they depend on different parts, so we decided to break them down to make them more reusable. For example, the inference will depend on a neural net framework, so and it doesn't depend on the model. And the tensor decoder is actually exactly the opposite. It will depend on the model, but not on the neural net framework. Like tracking, typically done with computer vision, but sometimes also with ML, so it will more depend on the acceleration and overlay and serialization. This is just example of element consuming analytics metadata, and that they actually don't depend. If the analytics results have been normalized, and we'll get to this part a bit later, they don't depend on the model and neither of the framework. So all this is to say that the elements are break down in parts to make them more reusable. One more to mention is sometimes we have the analytics result will be transformed into a media itself. So we can think of super resolution, for example, or TTS, STT, are example of that. And why would you use GStreamer for this? Well, I think if you're here, I think you have a good taste of what is GStreamer. 800 elements available. It's very efficient, so you can run this on embedded device. It has plenty of accelerated elements. It excels at networking. It has growing analytics support, and it's been around for a very long time and is still thriving. And I think it is not just a bag of tools. So it's actually all it's all the mechanism that make them work together. that make it very useful. And I think it's very useful to have this into an analytics pipeline. New and improved tool for analytics pipelines. So this is more about analytics meta. I think we heard the name of it during the State of the Union this morning. So analytics meta, it's a library that is based on GST meta, but it's made specifically for transporting analytics result. And the way it's done, it's reducing the allocation and the allocation that would happen if it was just using GST meta. One of the things that is done is that so the green box here is representing one GST meta, but actually it's just a container of memory that contains multiple analysis results. So when it's attached to a buffer that is coming from a pool, when it's returning to the buffer pool, instead of being deallocated, the data will just be invalidated. So next time that you have a new analysis that is done, this buffer is already allocated, and you can just reuse it. So eventually, you'll have during the initialization phase, you'll have a couple of allocation and resizing, but eventually, quickly you'll reach a constant regime where you have very little allocation happening. So yeah, each of the different green box can be a different analysis result, and the other special thing with analytics meta is that you can create relation between each result. So you're able, just as a very common example, you could have an object detection with a classification. So you can say actually which detection is directly related to a classification as opposed to, so there's a built-in mechanism to describe the scene using those relations. That was working well for analytics results that are, let's say, not very heavy when we think about classification, tracking, and object detection. But when we wanted to add support for segmentation. Segmentation is much more like grayscale image-like the result. So, and we wanted to take advantage of what existed in GStreamer, like the buffer pool for this. And so one idea was that, okay, if in each of the analytics meta, we can just reference a buffer that was taken from the buffer pool, but there's a catch there because, like I said earlier, when the analytics meta returned to the pool, it will just be invalidated. So there was no way to release the reference here. So what we've done here, if we added support for each type of specific meta can actually get an opportunity to clean up, do something before being when the buffer is returning to the pool. So based on this, we were able to add support for segmentation. So now there's a new, well, it's still MR, but it's going well. And so there's a new segmentation analytics meta, and on top of this, they're quite similar. There's a tensor analytics meta. So a tensor analytics meta is actually storing the result of the analysis, but in a model-specific way. So in other words, it hasn't been decoded yet. It can be useful for scenario where you have a multi-stage inference, like one of the model can be receiving the output of another one, and you would like to keep the relation between those buffer to be able to later on to do the tensor decoding, and so you know which one are related. So, and it can be used also as a general purpose way to store a blob of results and with a relation with something else. So now, like the new element in GStreamer that are with analytics capabilities related to analytics, so object detection overlay. We have a new tensor decoder for fast SAM YOLO V8 segmentation. So, and we have the segmentation overlay. We have the classification tensor decoder. We have support for PyTorch inference. So before we only had Onyx inference, now we have PyTorch and TF-Lite inference, which is one of the framework that is very popular on embedded device. And tensor decode bin, which is still a prototype, but very promising. So, this brings us to will bring us to the next topic. But yeah, last one, Onyx inference, we improved it. Before the the sync caps were sort of static and independent from the model that we were loading. So it wouldn't be able really to communicate to the upstream element what type of processing were needed. You would, when you were building your pipeline, you had to know, well, okay, this is the type of data you're expecting. So now what we've done is we're actually extracting the capabilities from the model and exposing them on the sync path. So if there's any pre-processing done and an element able to handle it, and in some cases it even can go back to the sensor itself and capture exactly in the format that is required for the inference. Tensor decoder and tensor negotiation and auto plugging of analytics element. Here I created a hypothetical segment of analytics pipeline where we have the pre-processing, inference again, a T, and couple tensor decoder. And let me just synchronize here. Yeah, so why we want to have a constraint on the tensor? Well, the whole idea is that we would like to be able to inform there's the tensor decoder that are at the end that knows of, that are able to interpret the result of the analysis, and those based on their capability, they can inform upstream element the inference that potentially one of the tensor is actually not required. Sometimes, like based on the pipeline you're creating, you might not need one of them. So that's one of the goal. Well, the main goal actually is also to be able to create a tensor decoder bin, because they are model specific. For each model you need a new one. So it would be useful to be able to have an abstraction of the tensor decoders to this way, if you're changing where you're running your pipelines, it brings more your portability to your pipeline. You're able to bring it to a different platform. If your tensor decoder use acceleration, then it will not, you won't have to change your application level. And yeah, that's pretty much the goal. So, and I don't know if you're able to. I don't know if we're able to see it, but in the capability described there's a new field called tensor. So I'll go into more detail into how this can be done. But for this, we'll have to, I'll just review a little bit the basic of capability in GStreamer. So what is this capability? If you were thinking this means actually can support anything, you're correct. And then this is a much more constrained environment. Just say we can support a raw video. And next one, in that case, we have a capability on A, the width is constrained. And then on B, we have the height is constrained. If we're intersecting A with B, really what is happening is we are intersecting the width of A with the width of B, which is any. And that's why we have the width. It's equivalent to the width of A, and the same goes in the other direction. If you're intersecting the B with A in terms for the height, we are intersecting the height of B with the height of A, which give you the height. So that's why you're ending up with a more constrained environment on C. And this whole idea is. The same concept will be used to negotiate tensor. Because they are independent. let's say, they are independent. What I wanted to show here is that width and height are independent, and the same idea is used with when you negotiate a tensor. So yeah. So oh yeah. So for tensor, the difference with width and height is just integer range, but for tensor it's composite capability. So it means that you will be describing multiple things inside it, and to describe this, we use one of the feature of GStreamer is able to have caps capability inside a capability. I'll do a quick review of what is a tensor. There's actually we don't call them like this in GStreamer, but we see them quite frequently. Well, its simplest form, not so much, just a scalar, but a vector. So we can think of audio stream, just a matrix like a grayscale image. Next one, a color image, and high dimensionality tensor. Well, they're kind of more used in the neural net world, and the data type. So those are the generic property of tensor. And so this information needs to be known by the tensor decoder to be able to interpret the results. But it was not like just those. It's not enough actually. So there's still, and I'll give you a very simple example to show that is that this is just bounding box object detection. On the left, you can see at the top that they have the same. They have exactly the same generic tensor properties, but in the first case, the bounding box is expressed as top left coordinate, width and height, and on the right side they're expressed as top left, bottom right. So this is just a very simple example to show that you need an additional information there to be able to interpret a tensor. And the way we use to describe this is to just give them an ID. And a bit later, we'll see how this is integrated into the capabilities. Here, we have two tensor. They have again the same capability, generic properties, and if we intersect, they still separate because they have a different encoding. The thing I was just referring to, the tensor ID. So if I show them here, so here's an example of a capability to represent the two tensor we were looking at before. So we have like the inner part, we have the generic property, and but there's a longer string there, which uniquely identify one tensor from the other. So when you intersect them, which is very important property during the negotiation, you'll have like, it's the equivalent of a union basically. And then those can be inserted in, you can have properties that are global to multiple tensor, for example, batch and model name. So those are integrated in the capabilities to express there. And then it goes to what we typically see with video. So with this, so once we've extracted the capabilities and expressed it on the before the inference, we have the pre-processing that can happen, and then there will be what to say, so each of the inference will basically add his what it can produce through his capability and negotiate with the tensor decoder at the end. So if you, in this case, I have an example where E is not produced, so you'll be able to detect that you have nothing upstream that can produce this and this would fail to negotiate, or and also it's opening the door to tensor decode bin where you can actually find that which tensor decoder that are available that able to handle what the inference element can produce and select them, which is actually exactly what we produced. We created there, so we can see that the process goes like this. We just all the tensor decoder are registered with the class tensor decoder. So when we get the caps from the upstream, we test each of the tensor decoder for if they would accept the caps. If they do, we add them to a list, and later on we rank them. It can be specific to a platform, and we've selected one tensor decoder for the pipeline. So yeah, I think that's pretty much around. I think. Is there questions? Yes.
There's some work that's happening on metadata by NVIDIA intelligence. Actually, there's a talk for similar question is asked. Is there any work happening on consolidating the different types of?
Yes, this is exactly this is the idea of this is all to bring it upstream. So many of those elements in library they are already available in the upstream GStreamer and eventually one of the goal of this is that you'll be able to move your analytics pipeline to a different platform, and you're going to stay with the platform because there's the acceleration that you want there. But if at some point in time you have different needs for any reason, you're not attached because you're using. Yep. Thank you.